Okay, so now we will solve an example using Cook's Toom algorithm. So the example is that 2 cross 2 linear convolution given by SP is equal to HP into XP, where HP is equal to H0 plus H1P and XP is equal to X0 plus X1P. We have to use Cook Toom algorithm to construct an efficient implementation for the given convolution. So talking about direct implementation, so the linear convolution can be expressed as SP is equal to HP into XP. That is already given. Okay, this thing is already given. So substituting the value of HP and XP, so HP is H0 plus H1P and XP is X0 plus X1P. Okay, opening the bracket, we get H0 X0 plus H0 X1P plus H1 X0P plus H1 X1P square, and that is H0 X0 plus H0 X1 plus H1 X0. P is common from this term, and at this point we have H1 X1 P square. Okay, so total number of multiplication is M0, M1 multiplication 1, M1, M2, M3 and M4. So total multiplication is 4 and addition 1, 2, 3, total 3 addition. So if we implement this convolution directly, total number of multiplication operations required are 4 and total number of addition operations required are 3. Okay, so now we will use Cook Toom algorithm to evaluate this efficiently in the sense that our aim is to reduce this multiplication operation, and addition might increase. Okay, so we can implement this using matrix also. So if SP is written as S0 plus S1 plus S2 P square, okay, so the order of SP will be 2, P into P. So we can express this using matrix form. So we can write this in a row matrix. So S0, S1, S2 is equal to H0 X0, S1 is equivalent to H0 X1 plus H1 X0, and S2 is equal to H1 X1, H1 X1. So we can break this matrix as it has two different, one from HP and second from XP. So I can further break this matrix. I have two different signals, X0 and X1. Okay, so I can separate them like X0 and X1. So it is a 2 cross 1 matrix, and for this matrix 3 rows are compulsory because I have 3 rows on the left hand side. So this will be a 3 matrix, and the column will be 2, so it will be a 3 cross 2 matrix. So first term is h0 x0, so this is h0, and the second term is 0, only one term h0 x0 is needed. Okay, so h0 into x0 plus 0 into x1, so that is h0 x0. At this point in second row we have h0 x1 h1 x0, so at this point I will have h1 multiplied by x0, and this is h0 x1, so here I will have h0, so h0 x1. Here only one term is needed, that is h1 x1, so corresponding to x1 I can have h1 at this point and 0 at this point. So this is a 3 cross 2 matrix, this is a 2 cross 1 matrix. So one more information is given to you, that beta 0 is 0, beta 1 is 1, and beta 2 is minus 1. Okay, so now using this information we will implement the linear convolution using Cook Toom theorem. So first step was to select the appropriate value of beta. So in this case it is already given, we don't have to select the beta. Okay, so this was the first step, we don't have to worry about this now. Second step says that calculate h of beta I and x of beta I for I equal to 1, 2 up to L plus n minus 2. Okay, so L is total number of terms in HP, n is total number of terms in XP, so both are having 2 terms respectively. So L is also equal to 2, n is also equal to 2. So 2 terms in XP and 2 terms in HP. So the value of L plus n minus 2 will be 2 plus 2 minus 2, that is 2. Okay, so for I equal to starting from 0, sorry. So for I equal to 0, 1 and 2, we have to calculate h of beta I and x of beta I. Okay, so for I equal to 0, 1 and 2, value of beta I is 0, beta 1 is 1 and beta 2 is minus 1. So h of beta I, that is given by h0 plus h1p, and x of beta I, that is given by x0 plus x1p. We have to place the value of beta into p. So for I equal to 0, beta I is equal to 0, so h of beta 0 will be h0. For I equal to 1, beta I is 1, so h of beta 1 will be equal to h0 plus h1, putting p equal to 1. And for I equal to 2, beta I is equal to minus 1, so it is h of beta 2 is h0 minus h1. Similarly, we will calculate x of beta I, so x of beta 0, putting p equal to 0, x of beta 0 is x0, x of beta 1 will be x0 plus x1, and x of beta 2 will be x0 minus x1. So the next step is to write s of beta I is equal to h of beta I into x of beta I for I equal to 0, 1 and 2. Okay, so s of beta 0 will be equal to h of beta 0 into x of beta 0. S of beta 1 will be equal to h of beta 1 into x of beta 1, and s of beta 2 will be equal to h of beta 2 into x of beta 2. The important point to be noted is that you have to just write in this way. You have to don't open the bracket and multiply. So just write, don't open bracket. Okay, so don't put h of beta I and x of beta I at this point and solve. You have to just write. Okay, so at this point you can see that total number of multiplications are 3. The total multiplications is 3. You need to evaluate s of beta 0, s of beta 1 and s of beta 2. Only 3 multiplications are needed. One is h of beta 0 into x of beta 0, second is h of beta 1 into x of beta 1, and third is h of beta 2 into x of beta 2. Okay, and at this point there was 4 number of multiplications. Okay, so in the last step you have to use Lagrange's interpolation formula. So from Lagrange's interpolation formula, you have to write s of p, that is given by s of beta naught into p minus beta 1, p minus beta 2 divided by beta naught minus beta 1, beta naught minus beta 2, plus s of beta 1 multiplied by p minus beta naught, p minus beta 2 divided by beta 1 minus beta naught, beta 1 minus beta 2, plus s of beta 2 multiplied by p minus beta naught, p minus beta 1 divided by beta 2 minus beta 1 and beta 2 minus beta naught. Okay, so solving this equation and rearranging the terms, we will have s of p is equal to s of beta naught plus p s of beta 1 by 2 minus s of beta 2 by 2 plus p square minus s of beta naught plus s of beta 1 divided by 2 plus s of beta 2 divided by 2. And in the left hand side I can write s of p is equal to s0 plus s1p plus s to p square, and right hand side is as it is. Okay, so I can express this in the form of a matrix. Okay, so on the left hand side I have three terms, s0, s1 and s2, and on the right hand side I have s of beta 0, second term is s of beta 1 by 2 minus s of beta 2 by 2, and third term is s of minus s of beta 0 plus s of beta 1 by 2 plus s of beta 2 by 2. So on the left hand side I have s0, s1, s2, and on the right hand side I have s of beta 0, s of beta 1 by 2 minus s of beta 2 by 2, and in the third row I have minus s of beta 0 plus s of beta 1 by 2 plus s of beta 2 by 2. Okay, so now I will break this matrix. So I have s of beta 0, s of beta 1 and s of beta 2, so I can separate this. Okay, so observe this last column because it is having all the terms. It is having s of beta 0, s of beta 1 by 2 and s of beta 2 by 2. So now I am going to separate the signals. It is s of beta 0, this is s of beta 1 by 2, so s of beta 1 by 2 and s of beta 2 by 2. So this is a 3 cross 1 matrix, and I have to have 3 rows. So the matrix, this matrix that I am going to create will have 3 rows, and number of columns will be also 3 based on this, based on number of row of this matrix. So 3 cross 3 matrix. Okay, so first at this point I can have 1, so 1 into s of beta 0 will be s of beta 0, and no other term is present, so remaining values are 0 and 0. So at this point in the second row I have s of beta 1 by 2 minus s of beta 2 by 2, so I don't need s of beta 0, so correspondingly I can put 0 at this point. S of beta 1 by 2, so plus 1, factor of plus 1, and s of beta 2 by 2 minus, so minus 1 at this point. And in the last row, minus of s beta 0, so minus 1, plus s beta 1 by 2, so plus 1 at this point, and plus 1 at this point. So s of beta I can be written as h of beta I into x of beta I. So I will substitute the s of beta with product of h and x. So s of beta 0 will be h of beta 0 into x of beta 0, s of beta 1 will be h of beta 1 into x of beta 1 divided by 2, and s of beta 2 will be h of beta 2 into x of beta 2 divided by 2. If further, this matrix consists of element from two different equations. First is h of beta I, second is x of beta I. So I can also separate this. So in the right hand side I will have 0 0 as it is, this matrix as it is, and from this I can separate x of beta 0, x of beta 1 and x of beta 2. So I can write a column matrix x of beta 0, x of beta 1 and x of beta 2. So for the element of H, this is a 3 cross 1 matrix, and for the element of H, the number of row is 3. This is mandatory. The number of column will be decided by number of row of this matrix, that is 3 cross 3. Okay, so 3 rows, 3 columns. Now I will decide the terms accordingly. This is h of beta 0, x of beta 0. So first value is h of beta 0 multiplied by x of beta 0. Remaining values are not needed, so 0 and 0. This is h of beta 1 into x of beta 1 by 2. So x of beta 0 is not needed, so 0. X of beta 1 is needed, so h of beta 1 divided by 2 into x of beta 1. This is not needed, so put 0. And x of beta 2 into h of beta 2 is needed, so put 0 and 0 in the first and second column, and at this point we have h of beta 2 divided by 2. So now at this point I can substitute the value of h of beta I and x of beta I into this matrix. Okay, so I have already calculated the values of h of beta I and x of beta I. I have to just substitute it accordingly. So h of beta 0 is h0, h of beta 1 is h of beta 1 is h0 plus h1 divided by 2, 0, and h of beta 2 is h0 minus h1 divided by 2, and similarly x of beta 0 is x0, x of beta 1 is x0 plus x1, and x of beta 2 is x0 minus x1. So at this point again two signals are mixed, x0 plus x1, x0 minus x1. Okay, so I will separate this in the form of x0 and x1, because x0 and x1 can be input to input signals. Okay, so just I need to substitute their values as it is. So this is a 2 cross 1 matrix, and this matrix should be a 3 is fixed, number of column will be 2, so this should be a 3 cross 2 matrix. Okay, so I have to fill the 2 columns for each row. So starting from row 1, x0 is needed, so putting 1 at this point. X1 is not needed, so 0. x0 plus x1, so plus 1 plus 1. x0 minus x1, so this is 1, this is minus 1. Okay, and the remaining values as it is. Okay, so what I am trying to do, I am trying to break this calculation in such a form that I just have to put the values of the given coefficients, that is h0 or h1 or x0 or x1, whatever are the values, and then they will be calculated using this precomputation matrix. So this is a precomputation matrix. This will add or subtract the signals x0 and x1, and these are constant coefficients h0, h1. Okay, so we can evaluate h0 plus h1, h0 minus h1 by 2 before starting the calculations, because these are constants, we already know these values, so they can be pre-evaluated. And this is post computation matrix. Okay, so final addition, this final addition will be achieved by the post computation matrix. So the sequence of the computation will be first this addition and subtraction of the constants coefficients can be pre-evaluated. So I can write capital H0 is equal to small h0, capital H1 is equal to h0 plus h1 by 2, and capital H2 is equal to h0 minus h1 by 2. So this will be pre-computed. No need to add or subtract them again and again, as they are constant. In the second step, this pre-computation matrix will combine these two signals that are coming from the output source. So x0 will be equal to small x0 as it is. Second calculation is addition of two signal x0 and x1. So capital X1 can be written as the sum of x0 and x1, and subtraction of the two signal x0 minus x1 can be written as capital X2 is equal to x0 minus x1. Okay, so these terms are pre-computed. Now we have to just put the values of the x0 and x1. So this matrix, pre-computation matrix, will generate the required result, and then we need to have the product of h of b0 into x of b0, and so we need to have product of h of bi into x of bi. Okay, so s0 can be written as h0 into x0, s of 1 can be written as h1 into x1, and s of 2 can be written as h2 into x2. Okay, so at this point, h of beta 0, beta 1, beta 2 is pre-computed. Pre-computation matrix has calculated the values of x of beta 0, x of beta 1, x of beta 2. Now we can multiply this two values. So these two, and at last we have to achieve this expression. Okay, so that will be done by this post computation matrix. So small s0 is simply s0, capital S0. Small s1 is s1 minus s2. Okay, so you can see that this is S1, this is S2, this term is S2, this is S1 minus S2, and small s2 is equal to minus s0 plus s1 plus s2. So minus capital S0 plus capital S1 plus capital S2. Okay, so at this point you can see that the number of multiplications is 3. These are the multiplication that are need to be performed, and total number of addition. Okay, so these are constants, these are pre-computed, so we will not consider this into addition operation. Okay, so this is first addition, this is a1, this is a2, this is a3, this is a4, and this is a5. Total 5 additions.